This segment talks about permutations. And here's an example. A permutation is an ordering of a list of things. So here we've got the list 1 to 4, and you can see in fact there are 24 orderings of that. That's 4 factorial, 4 times 3 times 2 times 1. Because there are 4 choices for the first element, 3 for the second, 2 for the third, and 1 for the fourth. Hence 4 factorial. Now, how can we build a list of all the permutations of a list? I'm going to describe 2 informal designs for doing this, and then give you a chance to think about that, and then I'll come on and show how they're implemented in Haskell. For our first example, let's take the list, just for example, A, B, C, D. So the first element of the list is A, and the rest of the list, the tail, is B, C, D. And suppose we want to define the permutations of x colon x's using the permutations of x's. So, for example, we have a permutation B, D, C of x's. How does that give rise to permutations of A, B, C, D? Well, we can think that there are 4 different places we could add the A. We could say something like A, B, D, C, or B, A, D, C, or B, D, A, C, or B, D, C, A. So that single permutation has given us 4 places that we might insert the final element to give us a permutation of A, B, C, D. So what we need to do is go from each permutation of x's to these permutations of the whole list, where we insert A in each of the possible positions in the list. So that describes informally one algorithm for producing permutations. In our second approach, let's again take the list A, B, C, D. And in this approach, we do something rather different. We think of a permutation like this. We think of choosing an element of the list, like B, and then we think of taking the remainder of the list, that's A, C, D, and taking a permutation of that. So, for example, giving us C, A, D. And then the permutation overall that we get is B is the first element, we've chosen it, and then we have a permutation of what remains. So you can think, I've talked in terms of choosing things. This is suggestive. It makes us think, if we have a non-empty list, x's, what we're doing here is we're choosing an x from x's, and we're choosing a p which comes from the permutations of remove x from x's. So we choose an x, in this case b, we choose a p from the permutations of a, c, d, and what we chose here was c, a, d, and the final thing that we produce as the answer is x colon p. And we can see this as a list comprehension for perms x's in the case if x's is not empty. X's is not empty. Otherwise, if x's is empty, then perms of the empty list, there's just one permutation, it's the empty list. So we've got a direct definition of a list comprehension algorithm choose an X for the first element, and then the rest of the list is got by permuting the remainder of the list. Now, I haven't defined the function to remove X from X's. That's a pretty straightforward. I remove the first occurrence that I find in the list. And I'm making the assumption here that when we're doing permutations of a list, the list contains different elements. There are no repeats. This algorithm wouldn't work properly if there were repeats, because I think our remove function would always remove the first, or a particular, the last or the first or whatever, of the X's in the list. In order to make this algorithm work, we have to not remove X, but we have to think about all the positions that X might occur in, and then remove X from those positions. It makes the algorithm different and, in a sense, more complicated. So the assumption here is that X's consist of distinct elements, and we're permuting those. And here we get the permutation by choosing the first element somewhere in the list and then choosing a permutation of what remains. And this gives us a Haskell algorithm for doing that. Let's go back to our first example now and recall how we did this. We get a permutation of X colon X's by getting a permutation of X's and then sticking X in every possible position we could. Now, how can we do that? Let's think about writing some Haskell to do that. We want to write a function, let's call it split add, that takes an element A and a list X's, and it adds A at every possible point that we could in the list X's. And if you think what that will look like, it will look like take n of X's plus plus A plus plus drop n of X's, where n is a value from 0 up to the length of X's. That will mean we're splitting that list at every possible position that we could. So here's our definition of split add. Again, we're making use of a list comprehension. And what we will now say is that the permutations of X colon X's are got by applying split add X to every element in perms X. So we need to map that on perms X's. So for each element in perms X's, we split add. So that gives us a list of lists of lists, and then we concatenate the result. And again, as in the previous case, the permutations of the empty list are just given by that single permutation. So what does this say? Let's just recall. It says for a non-empty list X colon X's, find all the permutations of X's, and then for each of those permutations, apply split add X to that permutation, and that will give us a list of lists, and then we concatenate to get a list of lists. Now, in fact, because I do the insertion here by position, this will work equally well for lists which have duplicates. So this is, in a sense, is a more durable algorithm. It doesn't assume all the elements in the list are distinct, because it splits the list up according to position and not according to content, as it were, which is what we did with remove in a way. Okay, so different algorithms with slightly different behavior on lists with repeated elements, but In both cases, when lists don't have repeated elements, they produce the list of all permutations. And if the list is of length n, that will be a list of length factorial of n.